Hey y'all, welcome to my course Python NumPy for your grandma. So easy your grandma can learn it. In this course, we're going to cover everything you'd want to know about NumPy, including array creation, broadcasting, indexing, random number generation, and a whole lot more. And we're going to do it through a combination of theory, examples, and practice problems. A couple things you need to know up front. 1. I'm using NumPy version 1.19.3. There's a good chance you're using a later version, but don't worry, it probably won't make a difference for 99% of what I teach in this course. 2. I'm using Google Colab as my IDE. Now, you don't need to use Google Colab, but if you want to, it's a really awesome free way to run Python directly inside your browser with essentially zero maintenance and zero hassle setting things up. So if that interests you, I have a free tutorial on how to set up and use Google Colab, which I'll link to in the course notes. All right, I'll see you in the next lecture. The primary data structure in NumPy is the n-dimensional array, so that's going to be the focus of this course. But before we start using arrays, let's motivate their existence. Suppose you have a lot of data, like the price of a stock measured every second for a year. That's about 32 million values. To represent this data in native Python, the most obvious data structure we could use is a list. Let's give that a go using arbitrary made-up stock prices. Okay, we'll say prices equals empty list, n equals 60 seconds times 60 minutes times 24 hours times 365 days, and for I in range n, prices.append 100 plus I divided by 100. And then we'll go ahead and print the first 5 prices. Okay, now let's go ahead and calculate the average stock price. So to do that, we could say average equals 0.0 for P and prices, average plus equals P divided by len prices, and then we'll go ahead and print the average. All right, and hopefully you noticed that populating our list of prices took a few seconds, and so did calculating the average price. Now, it wasn't agonizingly slow, but it would be if we had to do the same thing for hundreds of stocks. Now let's see how you could do the same sort of thing in NumPy. So here I'll import NumPy as in P, and then I'll say prices equals 100 plus np.arange n divided by 100. We'll go ahead and print the first 5 prices just like before. And then I can calculate the average as np.mean prices and print the average. Pretty easy and fast, right? The takeaway here is that NumPy arrays are fast, and that's the main reason they exist. All the convenient math functions, random number generators, and other things provided by the NumPy package are great, but secondary to the main benefit, the speed of the NumPy array data structure. So why are arrays faster than lists? And if that's true, why do lists even exist? First, you need to understand that NumPy arrays are intended to store objects with the same size and type. That's because arrays store data in contiguous, fixed-size memory blocks. For example, an array of 32-bit integers like 301 would internally be stored in binary like this. If you wanted to access the third element in the array, you can essentially say, hey computer, give me the third element of this array, and then your computer starts at the beginning of the array and knows exactly how many bits to jump across to get to the third element, in this case 64 bits. Knowing exactly how many bits to jump across to get to some requested element is what makes arrays fast for data access. Unlike integers, strings are objects that vary in size. For example, consider the strings, hello, I am a banana. The string hello is 40 bits, I is 8 bits, am is 16 bits, a is 8 bits, and banana is 48 bits. So unless we agree on a maximum possible string size, we can't easily represent these strings with contiguous, fixed size memory blocks because the strings are different sizes. And if you just store them in contiguous memory blocks like this, as soon as you start asking your computer to fetch a specific element, you'll run into problems because your computer doesn't know how far to jump from the beginning of the array to get to some requested element. Not to mention a host of other problems like what happens if we try to swap two elements with different sizes. To get around this complexity, we could store the strings in some random location in memory and then build an array of fixed size pointers to the strings. Now, a pointer is just an integer that identifies some location in your computer's memory, i.e. a memory address. So now if we want to fetch, say, the third element, assuming our pointers are 32-bit integers, just like before, we can quickly jump across 64 bits to get to the third pointer, and then make that one extra step to go retrieve our desired string element. The benefit to this architecture is that pointers can point to anything, so we could actually store a combination of strings, integers, and other objects all together. The downside is that you have to make that one extra step each time you want to fetch an element. Plus, the lack of a guarantee that all your data is the same type can cause bugs. For example, if you try to sum the elements and one of them turns out to be a string. This architecture I'm describing is one implementation of a list. So to recap, NumPy arrays are faster than lists, and that's why we like them. But that speed comes at the cost of being flexible. Specifically, if we have a NumPy array, each element of the array should be of the same type. That means we can have an array of ints, an array of floats, or an array of booleans, but not an array of ints, floats, and booleans together. Before we can start using NumPy, we need to install it and import it. The easiest way to install it is with pip. So pip install NumPy. But if you're on Google Colab like me, you'll need to do !pip install NumPy, where this exclamation mark just tells Colab you're running a shell command. Although you don't even need to do that because NumPy is already installed on Colab by default. So then to import NumPy, the convention is to import NumPy as np. All right, so we'll make our first array from a list of numbers. We'll say r equals np.array, open parens, list 10, 20, 30, 40, 50. Okay, we can print the array. We can check its dimensionality and its shape. So in this case, we have a one-dimensional array with shape what I'll call 5 by. We can see how many elements it contains with len. So in this case, 5. And if we wanted to make a two-dimensional array, we can do that too from a list of lists, like r2d equals np.array, open parens, and then I'll pass in a list of two nested sublists. So let's make this guy 10, 20, 30, 40, 50, 100, 200, 300, 400, 500. And just like before, we can print the array, check its dimensionality and its shape. So in this case, we have a two-dimensional array with shape 2 by 5, 2 rows by 5 columns. And we can see how many elements it contains. Now, you might be surprised to see that R2D has 2, not 10 elements. That's because R2D can be interpreted as an array that contains 2 arrays inside of it. If you want to get the total number of nested elements in the array, you can use the .size attribute like R2D.size, and in this case you get back probably what you expected, 10. If you want to know what type of data is in the array, you might try using Python's type function like type R2D, but this just tells you that the object itself is an int array. To see what type of data the array is actually storing, you need to use the .dtype attribute. And in this case, you can see that R2D is storing 64-bit integers. Now, there are 2 basic rules for every NumPy array. Every element in the array must be of the same type and size. And if an array's elements are also arrays, those inner arrays must have the same type and number of elements as each other. In other words, multi-dimensional arrays must be rectangular and not jagged. So for example, I can make a 1D array of integers, and this is fine because every element in the array is an integer. So for example, np.array 1, 2, 3, and like this checks out, no problems. Now, what if I try to make an array from a list that contains a mix of integers and strings? So np.array, open parentheses, 1, hello, 2. Okay. Now, in this case, NumPy doesn't error, but what it does is it casts the integers, and you can see that here. It casts the integers to strings in order to satisfy the property that every element is the same type. Now, you might also be wondering, hey, I thought you said you can't have an array of strings because strings are objects that vary in size, and the whole point of an array is to store fixed size objects. The caveat to what I said is that you can create an array of strings if you restrict the strings to a certain size. And that's what's going on here. The dtype left caret U21, that stands for Unicode strings with 21 characters or less. So if we take this array and let's say we set it as a variable foo, and we can print foo. So now let's say we try to reassign the first element of foo to a really long string. Now let's take a look at foo. So you can see our really long string actually gets truncated down to 21 characters. All right, so what if we try to build an array from a list of lists where the first inner list has 4 integers and the second inner list has 4 floats, like np.array, open parentheses, list, and then we're going to have 2 nested sublists where this one has 4 integers and this guy has 4 floats. Okay, so once again, NumPy doesn't error, but what it does is it promotes these integers to floats, and that's to maintain that homogeneous data type. All right, so let's see one last example. What if we try to build an array from a list of lists where the first inner list has 4 integers and the second inner list has 2 integers? So I'll say np.array, open parentheses, list, and then this first nested sublist has 4 integers and the second nested sublist only has 2 integers. Okay, so in this case, NumPy gives us a warning that says creating an ND array from a ragged nested sequences is deprecated, but we actually do get back an array with dtype object. Now, this just means you have an array of pointers, which is more or less the same thing as a standard Python list. In this video, we'll look at different ways to create a NumPy array. As we saw earlier, you can make an array by typing np.array, open parentheses, and then passing in a list of values like A, B, C. Okay. You can also make a 2-dimensional array from a list of lists, and I'll copy and paste some pre-written code. So just like this, we have a list of 3 nested sublists, and we get a 3x2 array. And similarly, you could make an array, a 3-dimensional array from a list of lists, just like this. Now, let's say you want to make a 3x5 array filled with zeros. This will be a good time to check out the NumPy documentation. So I'm going to go to Google and search for NumPy array of zeros. And it turns out there's this function called zeros that does exactly what we want. Return a new array of given shape and type filled with zeros. And looking at the function signature, the only argument that doesn't have a default that we'll need to pass in is the shape, which can either be an int or a tuple of ints. So for example, I'm going to go ahead and type np.zeros shape equals 3. And in this case, I get back a 1-dimensional array of 3 zeros. Similarly, I could do np.zeros shape equals 3x5. And in this case, I get back a 3x5 array filled with zeros. Now, what about the generic case? So say instead of zeros, you want to fill a 3x5 array with the word cat. So again, let's hop over to Google and we'll search for NumPy array filled with value. And it turns out there's a function for that as well called full. So this returns a new array of given shape and type filled with fill value. So pretty much the same thing, except we need to pass in a fill value. So here I'll do np.full. We'll say shape equals tuple 3, 5, and we'll set the fill value as the string cat. Okay, and then we get a 3x5 array of cat. So another very common array to build is a sequence array, like 1, 2, 3, 4. Now the function for this is np.arange, where you pass in start, stop, and step values. So for example, here I'll do np.arange, and we'll set start equal to 1, stop equal to 5, and step equal to 1. Okay, and then we get back the array 1, 2, 3, 4. Now notice that start here is inclusive and stop is exclusive. Alternatively, if you just type np.arange and then pass in some integer like 10, you'll get back the sequence array that has 10 integers and starts at 0. Okay. Now, by the way, the name arange stands for array range because it's like the array version of the Python range function. Now, another useful function is np.random.randint, which lets you build an array of random integers selected with replacement. So here I'll make a 2x3 array of random ints between 1 inclusive and 7 exclusive. We'll do np.random.randint low equals 1, high equals 7 exclusive. So the random numbers are going to go between 1 and 6. And then we'll set the size as 2x3. Okay, and you can kind of interpret this as like 2 iterations of rolling 3 dice. Now, obviously, there's a bunch of other methods to build arrays, and we'll see a lot of them later in the course. But hopefully this was enough to get your feet wet and introduce you to the NumPy documentation. In this video, we'll look at how to index a 1D array to access and modify its elements. We'll start by making a 1D array called foo with 5 elements. So here I'll say foo equals np.array, open parens, list, and then our favorite array, 10, 20, 30, 40, 50. And let's go ahead and print foo after we build it. All right, now we can access the ith element just like a Python list using square bracket notation, where the first element starts at index 0, and the second element starts at index 1, and so on. So for example, if I do foo square bracket 0, I get the first element, and foo square brackets 1 gives me the second element, and so on. Now, if we want to modify an element, say we want to change the second element to 99, then we can just type foo square brackets 1 and then equals what we want to change it to, like 99. Now, if I print foo, you can see that it updated. Now, since we know foo has 5 elements, if we wanted to access the last element, we could do foo square brackets 4, and we get back 50. Now, if we want to make that more dynamic, we could replace the index 4 with len foo minus 1. But we can do even better than that using negative indexing. So just like Python lists, the index -1 returns the last element in the array. The index -2 returns the second to last element. -3 returns the third to last element, and so on. And if we try to access an element outside the bounds of the array, like foo square brackets 999, we'll get an out of bounds error. If we want to access multiple elements at once, we can do that too, using a list or NumPy array of indices. So for example, I can say foo square brackets and then pass in a list like 0, 1, 4. In this case, I get back the first, second, and fifth elements in the array. Or we could do foo square brackets and then pass in a list like 0, 1, 0, 1 with repeated values, just to show you that the indices don't need to be unique. we could even pass in something like np.zeros and build a NumPy array of indices. So I'll say np.zeros shape equals 3. Well, maybe not. So the problem here is that the zeros function returns an array of floating point zeros by default, and indices need to be integers or boolean. We'll talk about that later. So if I print np.zeros shape equals 3, you can see these decimals here, and that indicates that these are floating point values. And if we go back to the zeros function documentation, you can see by default there's this argument called dtype that's set to float. So we need to make these guys integers, and there's a few different ways to do that, but I'll use dtype equals open quotes int 64 to make these guys 64-bit integers. And now I can just pass that into the square brackets here, and now it works. And so it basically returns the first element 3 times. All right, now another thing we can do is use slicing, just like Python lists. The signature here is basically foo, square brackets, start index, colon end index, colon step size. And there's a lot of shorthands to this, so let's look at some examples. So if we do foo colon, excuse me, foo square brackets colon 2, we get back every element from the beginning of the array to index 2 exclusive. If we do foo square brackets 2 colon, we get back every element from index 2 to the end of the array. And if we do foo square brackets colon colon 2, we get back every other element from the beginning of the array to the end. In other words, we get back the elements at indices 0, 2, 4, and so on. Another thing we can do is modify multiple elements at once. So for example, here we'll set foo square brackets indices 0, 1, 4 equal to the values 100, 200, and 400. And then let's go ahead and print foo after we do that. So you can see foo updated as we told it to. But in this case, our list of values, it needs to be the same size as our list of indices, unless we assign to a single value, in which case it gets applied to every index. So for example, if we say something like foo square brackets and then pass in a list of indices like 0, 1, 4, just like before, but this time we set it equal to the list 1, 2. Well, these are not the same size, so in this case, NumPy is going to throw an error, specifically a shape mismatch error. But what would work is if we do something like this, and in this case, even though they're not the same size, the value 1 gets assigned to each of these indices. In this video, we'll see how to index and modify multidimensional arrays. We'll start by making a new 3x4 array called bar from a list of lists. Before we start accessing elements from this array, it's important to understand its structure. Internally, bar is just a contiguous block of memory storing some data. Since we defined bar using a list of lists, NumPy makes it a 2-dimensional array, giving it 2 axes for indexing its values. Since this array has 2 axes or dimensions, NumPy knows to interpret our data as a rectangular array, where axis 0 is the row axis and axis 1 is the column axis. This means we can subset bar using a combination of row indices and column indices. Let's see some examples using the 2D array we just created. So if you want to get the element at index 1, 2, you can just do bar square brackets 1, 2. If you want to get the entire first row as a 1D array, you can do bar square brackets 0. Remember, bar can be interpreted as an array of arrays, so the first element of bar is just a 1D array. Now, if you wanted to get the entire first row as a 2D array, you can use the none keyword for the column index, like bar square brackets 0, none. We'll learn more about the none keyword later. Alternatively, you can use slicing for the row index, like bar square brackets colon 1. This is like saying, give me every row up to but excluding the second row, the row at index 1. And if you're feeling fancy, you can combine slicing, lists of indices, and negative indexing like this. Bar square brackets 1 colon 3, square brackets -2, -1. And this is like saying, give me the values between rows 1 and 3 exclusive, and the second to last column and the last column. And of course, you can make modifications. So for example, we could replace the top left element of bar with -1 like this. Bar square brackets 0, 0 equals -1. Or we could replace the second row with the third row like this. Bar square brackets 1 equals bar square brackets 2. Or we could insert zeros along the diagonal, like bar square brackets 0, 1, 2, 0, 1, 2 equals 0, 0, 0. Notice here that the ith row index and the ith column index combine together to select a specific array element. For example, row index 1 combines with column index 1 to select this element of bar, which we replace with this value. Alright, so we've taken a hard look at indexing a two-dimensional array. What about 3 and higher dimensional arrays? I suspect many people, including my former self, interpret three-dimensional arrays as rectangular prisms like this. The problem is that this spatial model breaks down when you go above 3 dimensions. So a better mental model, in my opinion, is when you have a one-dimensional array, think of a row of numbers. When you have a two-dimensional array, think of a matrix, so rows and columns. When you have a three-dimensional array, instead of thinking of a rectangular prism, picture a row of matrices. Then when you get to 4 dimensions, you can imagine a matrix of matrices. And it's easy to see how you could expand this to any number of dimensions. Now, if you have a 3-dimensional array, like this one called zoo that I have pre-written here, and you make an assignment like, let's say, zoo square brackets 0, colon, 1 equals 5. It's easy to picture the result before you see it because you can interpret this assignment as saying, set the first matrix, every row, the second column equal to 5. So now if we print zoo, you can see that's exactly what it did. It picked out the first matrix, every row, but only the second column, and updated those values to be 5. So everything we've looked at for indexing a two-dimensional array can be carried over to 3 or higher dimensional arrays. Now, for the sake of full disclosure, I'm actually glossing over some gritty details and complex scenarios, which I'll cover later when we do advanced array indexing. And if you don't finish this course, I highly recommend you watch that lecture before you bow out. But at this point, my goal is to cover the basics of array indexing so that we can start working with arrays in a meaningful way. In this video, we'll take a look at some basic math operations between arrays. We'll start by defining a pair of 2x2 arrays, foo and bar. If we add foo plus bar, watch what happens. The values of foo and bar get added element-wise. This pattern of element-wise addition holds true for every math operation between identically sized arrays. For example, if we subtract foo minus bar, it does element-wise subtraction. If we do foo times bar, it does element-wise multiplication. And if we do foo divided by bar, it does element-wise division. Now, what if you wanted to do matrix multiplication instead of element-wise multiplication? You can do that too using the @ symbol, like foo @ bar. Now, suppose we want to add a scalar like 5 to each element of foo. You might be inclined to build a 2x2 array filled with 5s, and then carry out the addition, like foo plus np dot full shape equals 2x2, fill value equals 5. And you can see this works, but it's overkill. In this case, all you need to do is foo plus 5, and NumPy will add 5 to each element of foo. The same goes for subtraction, multiplication, division, and all other binary arithmetic operations. In this video, we're going to do the first of many challenges. Now, I tried to make these challenges align with what we've already learned, but in some cases the solution requires a new function or trick that we haven't discussed. Now, that's on purpose because in the real world, the problems you come across aren't limited to the things you've already seen. So part of being a good data scientist is having the ability to search for a solution online and to read and interpret documentation. So I'm going to encourage you to do all of those things in your attempt to solve these problems. All right, let's get started on the first challenge. With your high school reunion fast approaching, you decide to get in shape and lose some weight. You record your weight every day for 5 weeks, starting on a Monday. Given these daily weights, build an array with your average weight per weekend. So here's the setup. Basically, I just import NumPy, and then I build an array of weights. So this weight here was recorded on a Monday. So then you have Tuesday, Wednesday, Thursday, Friday, Saturday, and Sunday. So your solution should be a 5-element array, 1 element per weekend, where, for example, the first element in your resulting array should be the average of these 2 values because this is the first Saturday and Sunday. It's the first weekend. So go ahead and pause the video and see if you can solve this problem. All right, so as they say, there's 1,000 ways to skin a cat. Here's the solution that I came up with. So let's go ahead and break this apart. So this piece here gives me the weight on every Saturday. And the way to read this is it's saying start at index 5, go until the end of the array because we leave the stop parameter empty here, and step by 7. So this is just basic slicing. And if we step by 7 starting from this value here, that's going to give us our weight on every Saturday. So then we can basically just copy that and tweak it to get our weight on every Sunday. And now we have 2 same-sized arrays, so we know we can add these together and their elements get added element-wise. So this gives us like the total weight per weekend. And then we can just wrap that in parentheses and divide by 2. Remember, this division gets applied to each element of the array. And that gives us our average value per weekend, which is our desired solution. After binge watching the Discovery Channel, you ditch your job as a trial lawyer to become a gold miner. You decide to prospect 5 locations underneath a 7x7 grid of land. How much gold do you uncover at each location? So here's the setup. You get 2 matrices. Gold is the 7x7 grid of land that says how much gold is under each location, and lokes is the prospect locations. So for example, the first row here indicates that you're going to prospect under row index 0, column index 4, which corresponds to this value in the gold matrix. Go ahead and pause the video and see if you can figure out how much gold you'll get at each prospect location. All right, so here's the solution that I came up with. Let's go ahead and break this down. So the first prospect location is 0, 4. So how would we determine how much gold is under this location manually? Well, what we can do is we can say gold, square brackets, and then just plug in row index 0, column index 4. And if we want to figure out how much gold is under the next prospect location, we can do essentially the same thing, except we'll use row index 2 and column index 2. And we get back 6. That's going to be this guy here. So how would we do this in one fell swoop? If you remember, what we can do is we can say gold square brackets and then pass in a list of row indices and a corresponding list of column indices. So in this case, our row indices are going to be 0 and 2, and our corresponding column indices are going to be 4 and 2. And this gives us the array 2, 6. So now the question is, how do we do this dynamically instead of manually? Well, notice that this list of row indices corresponds to the first column of lokes, and this list of column indices corresponds to the second column of lokes. So the real question is, how do we get back the first column of lokes as a 1D array and the second column of lokes as a 1D array? And the way we can do that is we can say lokes square brackets colon comma 0. And this essentially says, give me every row from the lokes array, but only the values at column index 0. And then we can make a little tweak to get column index 1. So now all we have to do is take this as a framework and then overwrite our row indices with this guy and overwrite our column indices with this guy. And that gives us our desired solution. You decide to invest in a series of billboards along Interstate 10 to advertise your stylish new chicken restaurant, Chic-fil-a. You buy 3 billboards evenly spaced, starting on mile marker 17 and ending on mile marker 28. Then you buy another 3 billboards evenly spaced, starting on mile marker 32 and ending on mile marker 36. In order from mile marker 17 to 36, your billboards display these ads: ABC, CBA. Determine how far each C ad is from your restaurant, which is located at mile marker 30. All right, so here's my solution. Now let's go ahead and break this down. So let's start by thinking about the first 3 ads. They're evenly spaced between mile marker 17 and 28. So it'd be useful if we had a tool that gave us an array of evenly spaced numbers from a start point to an end point. So let's go ahead and search Google to see if something like that already exists. So we'll say NumPy array of evenly spaced numbers. And sure enough, there's a function called linspace that returns evenly spaced numbers over a specified interval, where you give it a start, stop, and num parameters. So let's go ahead and play with that for a little bit. So I'll say np.linspace, and let's set start equal to 0, stop equals to 10, and num equal 5. So in this case, we get back a 5-element array from 0 to 10. Notice that the start and stop values here are inclusive. Now, another thing we can do is the start and stop values can be array-like values. So for example, I can set start equal to the list 0, 5 and stop as the list 10, 15. And in this case, I get back a 2-dimensional array where each column is a sequence. So for example, the first column is the sequence from 0 to 10, and the second column is the sequence from 5 to 15. Now, another parameter for linspace is axis, which by default is 0. And that means that these sequences span axis 0, the row axis. Personally, for our setup, I think it's a little bit more intuitive to use axis 1, where we can think about the billboards spanning the columns of this array. So if we want to make this match our framework, our problem, we can set the start parameters here as mile marker 17 and mile marker 32, and the stop parameters as mile marker 28 and mile marker 36. And of course, num in this case needs to be 3. So this array here represents billboards A, B, C, CBA, and where they're located. So now if we want to get the distance from each billboard to our restaurant, which is at mile marker 30, we can just take this and subtract 30. And this is close, except that we don't like negative values for distances. So let's see if NumPy has an absolute value function. Of course it does. Notice that there's a shorthand np.abs. So what we can do is we can just wrap this in np.abs, and this gives us back the absolute value or the distance from each billboard to our restaurant. So then the last thing to do is, well, we want to know how far each C ad is from our restaurant. Well, the C ads are going to be located here and here. So we just have to pick out the indices for those guys. So in this case, what we can do is we'll pass in a list of row indices and a corresponding list of column indices. So the row index for this guy is going to be 0. And the row index for this guy is going to be 1. And the column index for this guy is going to be 2. And the column index here is going to be 0. And then that gives us our desired solution. Of all the challenging concepts in NumPy, the one that's most crucial to wrap your head around is probably broadcasting. In this video, we'll see how broadcasting works and why it's useful. So, what is broadcasting? Well, we've already seen it in action, although you might not have picked up on it. When we add a scalar to a 1D array like this, the scalar gets added to each element of the array. In essence, NumPy is expanding the scalar into a 3-element array and then doing element-wise addition between the arrays. Of course, under the hood, NumPy doesn't actually do this because it'd be horribly inefficient, but in essence, that's what's happening, and that's an example of broadcasting. In 2 dimensions, you can imagine we have a matrix of values, foo, like this, to which we'll add a 1D array, boo, with the same number of elements as our matrix has columns. And in this case, NumPy carries out the addition as if it first copies boo along a new vertical axis to match the shape of foo, and then carries out element-wise addition. Now, what if boo had 2 elements? Perhaps NumPy would add boo to each column of foo. Nope. In this case, we get an error. So how does broadcasting work and when can we use it? Formally speaking, suppose we want to add 2 arrays, A and B. Moving backwards from the last dimension of each array, we check if their dimensions are compatible. Dimensions are compatible if they are equal or either of them is 1. If all of A's dimensions are compatible with B's dimensions, or vice versa, they're compatible arrays. Informally speaking, I think it really helps to visualize the arrays you're working with and how they'd expand for element-wise operations. Let's see some examples. Here, A is a 3x4 array, and B is a 3x1 array. We start by comparing the last dimension of each array. Since the last dimension of A is 4, and the last dimension of B is 1, NumPy can expand B by making 4 copies of it along its second axis. So these dimensions are compatible. Now we have to compare the first dimension of A and B. Since they're both 3, they're compatible. The only thing left for NumPy is to carry out whatever procedure we wanted on 2 equivalently sized 3x4 arrays. And remember, NumPy doesn't actually expand B like this because it'd be horribly inefficient. Let's see another example. Here, A is a 4x4 array and B is a 2x1 array. The last dimension of A is 4 and the last dimension of B is 1. So these dimensions are compatible. And just like the last example, we can temporarily transform B by making 4 copies of it along its second axis. Now we compare the first dimension of each array. In this case, there isn't an obvious way to expand B into a 4x4 array to match A, or vice versa, so these arrays are not compatible. Let's see another example where A has 3 dimensions and B has 2 dimensions. So, as before, we start by comparing the last dimension of each array. In this case, A is 4 and B is 1, so we can expand B into a 2x4 array, making these dimensions compatible. Next, we compare the second to last dimension of each array. In this case, A is 1 and B is 2. This time we expand A, copying it twice along its second axis to match B. At this point, we're out of B dimensions, so we know A and B are compatible. To complete our mental model of how math between these arrays would work, we can imagine copying B 3 times along a newly added first dimension. We're left with 2 transformed arrays, each with shape 3 by 2 by 4, which we can easily add or subtract or combine in some other way. Before I close out this lecture, I just want to say that when I do this sort of broadcasting expansion process in my head, I don't actually go through this formal process thinking of the shape tuples. I just kind of visualize the shape of these arrays, and I visualize how they'd expand into identical sizes. If you just look at this setup, it's kind of intuitive to see that A has 3 matrices, so we know B is going to be copied into 3 matrices, and B has 2 rows, so we know that A's matrices are going to expand into 2 rows, and since A has 4 columns, B's single column is going to get copied into 4 columns, and all of this works out pretty nicely. So that's sort of how I do this in my head and what my intuition is for broadcasting. In this video, we'll see how to use the newaxis keyword to increase the dimensionality of an array and why that's useful. Suppose you have these 2 arrays, A and B, and your goal is to build a 4x3 difference matrix where element ij gives ai minus bj. In other words, your goal is to subtract each element of B from each element of A. If you do A minus B, you'll get an error because the arrays don't have compatible shapes, and even if they were the same size, NumPy would just do element-wise subtraction, which isn't what we want. However, imagine if A was a 4x1 array and B was a 1x3 array. In this case, NumPy would use broadcasting to, in essence, turn them both into 4x3 arrays, and then carry out the element-wise subtraction that we want. So the question is, how do we convert A into a 4x1 array and B into a 1x3 array? Surprise, surprise, you can use np.newaxis for that. So if we do a square brackets colon comma np.newaxis, it inserts a new axis behind A's existing axis. In other words, it converts A from a 4x array into a 4x1 array. And then if we do b square brackets np.newaxis comma colon, it inserts a new axis in front of B's existing axis. In other words, it converts B from a 3x array into a 1x3 array. And now we can just carry out the subtraction to get our desired difference matrix. Note that newaxis is just an alias for the none keyword, so you'll often see people, including myself, use the none keyword here. In this section, we'll see how to use the reshape function to change the shape of an array. Suppose we have a 1D array called foo with 8 elements. We can reshape foo into a 2x4 array using either the .reshape method of the array object or the free function np.reshape. These methods implement the same logic just with slightly different interfaces. With foo.reshape, we can pass in the new dimensions individually, like this, instead of as a tuple like this. But this comes at the expense of not being able to specify the new shape keyword. So you couldn't do something like this, or you'll get an error. Okay, now let's go ahead and set bar equal to foo.reshape 2, 4, and we can print bar. And now let's reshape bar from a 2x4 array into a 4x2 array. We can do this in 2 different orders. So first we'll call bar.reshape, and we'll reshape it into a 4x2 array, and we'll set order equal to cap C. This implements C style or row major order, which reorders the first axis first. Alternatively, you can do the same thing with order equals cap F, which implements Fortran style or column major order, which reorders the last axis first. Let's see that again, except this time we'll reshape bar into a 2 by 2 by 2 array. So here's the C-style order. And then here's the Fortran style order. Now, a quick tip is when you reshape an array, you can use -1 for exactly one of the new shape dimensions, and NumPy will calculate it for you. For example, if we do bar.reshape 4 comma, and I don't even want to think about what that next dimension needs to be, I can just say -1, and NumPy will calculate that, oh, I need a 4 by 2 array. And this turns out to be super convenient and really handy. I use it quite a bit. Now, another thing to note is that in all these examples, we're creating a copy of the existing array. So when we do something like bar.reshape 4 comma 2, it doesn't actually modify bar. You can see if I print bar, bar hasn't changed. Instead, what it does is it creates a new array with new data. So if I wanted to modify bar and actually make those changes stick, I could say bar equals and then bar.reshape 4 comma 2. But this still actually creates an unnecessary copy before it makes this assignment. So a better way to do this is just to explicitly set bar.shape equal to the tuple 4 comma 2. And if we do that, you can see it actually modifies bar. All right, and then the last thing I want to cover here is the array transpose. So if you want to get the transpose of bar, you can say bar.capt or use the free function np.transpose bar. And the way to interpret this in higher dimensions is, let's say you have a 2 by 3 by 4 by 5 array. This transposes into a 5 by 4 by 3 by 2 array, where element I, j, k, l in the original array maps to element l, k, j, i in the transposed array. One of the most powerful features of NumPy is Boolean indexing. In this video, we'll see how you can use an array of Boolean values to index another array. For example, suppose we have this 3 by 3 array of positive integers called foo, and we'd like to replace every 3 with a 0. Running foo equals 3 gives us a 3 by 3 array of Boolean values, which I'll store in a variable called mask. Now we can use this array of Boolean values to index our original array, identifying which elements are 3 and setting them equal to 0. Just like integer arrays, you can use 1D Boolean arrays to pick out specific rows or columns from a 2D array. We'll start by making a couple length 3 Boolean arrays to select rows and columns from foo. So here we'll return rows 1 and 3, and here we'll return columns 2 and 3. However, watch what happens when we combine these row and column selectors together. You might be surprised to see that the result is the 1D array 9, 1. That's because NumPy treats Boolean indices like integer indices, where the integers used are the indices of true elements. In other words, NumPy treats the Boolean index array true, false, true, just like it treats the integer index array 0, 2. And NumPy treats the Boolean index array false, true, true, just like it treats the integer index array 1, 2. So when we selected rows 1 and 3 with our Boolean index, it's the same as if we had used the integer row index 0, 2. And when we selected columns 2 and 3 with our Boolean index, it's the same as if we had used the integer column index 1, 2. And when we combine these indexes, it's just as if we had used a combination of integer indexes, which, if you remember, selects elements based on corresponding indices. In this case, it's the pair of elements 0, 1 and 2, 2. Logical operators let us combine Boolean arrays. They include the bitwise AND operator, the bitwise OR operator, and the bitwise XOR operator. We can also negate a Boolean array by preceding it with a tilde. Let's see some examples of how you might use Boolean indexing in practice. Here we have an array of person names and corresponding arrays for their age and gender. With Boolean indexing, we can answer questions like, who's at least 44? Which we can do by setting ages greater than or equal to 44, and using that resulting Boolean array to subset the names array. Or which males are over 42. In this case, we build a Boolean array that identifies males and a second one that identifies people over 42. And then we use the bitwise AND operator to combine them into a single Boolean index. Or we could determine who's not a male or who is younger than 43 by doing nearly the same thing, except we'll use a tilde to negate the first Boolean array, and we'll use a pipe for our bitwise OR operator. And of course, here we set ages less than 43. Note that when we combine multiple Boolean expressions, we have to wrap each expression in parentheses, so that the expressions get evaluated before the bitwise logical operators. In this video, we'll see how you can use nan to represent missing or invalid values. Nan is a floating point constant that NumPy reserves and treats specially. For example, consider this array called bot, which contains 2 missing values. If you want to identify which elements of bot are nan, you might be inclined to do something like bot equals np.nan, but the result might surprise you. NumPy designed nan so that nan equals nan returns false, but nan not equals nan returns true. This is because equivalence between missing or invalid values is not well defined. In practice, this behavior prevents silent bugs from creeping into your program. In order to see which elements of bot are nan, you can use NumPy's isNan function. It's important to note that nan is a special floating point constant, so it can only exist in an array of floats. If you try to insert nan into an array of integers, booleans, or strings, you'll get an error or unexpected behavior. In this video, we'll see how you can represent infinite values in NumPy. Like nan, NumPy reserves floating point constants for infinity and negative infinity that behave specially. If you want to insert these values directly, you can use np.inf and np.nymph. More commonly, these values occur when you divide by 0. All the special behaviors that you might expect for these values exist, such as multiplying infinity by a positive constant equals infinity, adding infinity to infinity equals infinity, subtracting infinity from infinity has undefined behavior and produces nan, and dividing infinity by infinity has undefined behavior and produces nan. Unlike nan, positive infinity equals positive infinity, and negative infinity equals negative infinity. So if you have an array with infinite values like this one, you can find them just by checking equals positive infinity or equals negative infinity. Alternatively, you can use the functions isPosInf, isNegInf, and isInf. In this video, we'll see how you can use NumPy's random module to shuffle arrays, sample values from arrays, and draw values from a host of probability distributions. And then we'll see why everything I just showed you is deprecated and how to update it to modern standards. Let's see an example of how you might simulate rolling a 6-sided die 3 times. In other words, we want to draw 3 integers from the range 1 to 6 with replacement. For this, we can use the randint function from NumPy's random module. So here I'll say np.random.randint, and I'll pass in low equals 1, high equals 7 because the high value is exclusive, and size equals 3 because we want to sample 3 values. If you try running this on your machine, you'll probably get something different than I did. However, we can get reproducible results by setting a random number seed immediately before we generate random numbers. To set a seed, use the seed function with your favorite value passed in. So for example, here I'll say np.random.seed and pass in the value 1, 2, 3. And now if you copy and run this code exactly as I did, you should get the same exact answer here. Now, what if we wanted to draw 3 values between 1 and 6 without replacement? For this, we can use the choice function, giving it a 1D array of values to choose from, the number of samples we want to draw, whether values should be replaced, which is false by default, and a 1D array of probabilities corresponding to our 1D array of values, which by default gives equal probability to each option. So choice is like a generalized version of randint. Let's see some examples. First, we'll draw 3 ints between 1 and 6 without replacement. So I'll say np.random.seed, and let's set a seed 2357. And then we'll go ahead and say np.random.choice, and let's pass in a equals np.arange 1, 7. So remember, this is the array 1, 2, 3, 4, 5, 6, because 7 is exclusive. And then we can say size equals 3 because we want to sample 3 values. Replace equals false because we want to sample without replacement. And p equals none, just to be explicit about the fact that we want each value to be sampled with the same likelihood. Okay. Now let's do the same thing, but this time let's give a probability to each element. So here I'll say p equals, and then we'll pass in a list, or actually we can do an array. So np.array. And the important thing here is that your array should have the same number of elements as the array of values, and then the array of probabilities should sum to 1. So I'll say 0.1, 0.1, 0.1, 0.1, 0.3, and 0.3. So we'll give a little bit more likelihood to 6 and 5. All right. And then just to show, the flexibility of this function, let's go ahead and draw 3 elements from an array of strings. So I'll say np.random.choice, and here I'll set a as np.array. You can use strings too. And let's go ahead and sample 3 values without replacement. Now, what if you wanted to sample the rows from a 5x2 array like this one? You can use randint and choice for that too. The trick is to generate a random 1D array of row indices and use that result to select rows from the array you want to sample. So for example, we can use randint to sample 3 rows from foo with replacement. So here I'll say np.random.seed and pass in 1, 2, 3, 4. And then we can say rand rows equals np.random.randint. And then we want to sample values from the set of possible row indices of foo. So in this case, the row indices are 0, 1, 2, 3, and 4. So we'll say low equals 0, high equals 5 because the high value is exclusive, except let's make that more dynamic. So we can say foo.shape square brackets 0, and then size equals 3 because we want to sample 3 values. So let's go ahead and then print the rand rows. So we get back the array 3, 4, 4. And now if we pass this in to foo square brackets, we'll get back an array of random rows of foo selected with replacement. Now, if we wanted to do the same thing and select rows of foo without replacement, we can do nearly the same thing, except this time we'll use the choice function. So we'll say np.random.seed 1, 2, 3, 4. Rand rows equals np.random.choice. And now we'll pass in a as the set of possible row indices. So we'll say np.arange from 0 up to foo.shape0, the number of rows in foo. We'll set replace as false because we want to sample without replacement. And again, we'll set size equal to 3. We'll print rand rows. So now we get back the random row indices 401. And again, we can use that to subset foo. You can also use this technique to shuffle an array, but NumPy makes this even easier with a function called permutation. So for example, if we call np.random.permutation, open parens foo, we get back a copy of foo with its rows shuffled. Unfortunately though, permutation only shuffles the data along its first axis, so we couldn't use it to say shuffle the columns of foo, only the rows. We can also sample values from a variety of probability distributions. For example, if we wanted to sample 4 values from the uniform distribution between 1 and 2 to populate a 2x2 array, we can do that with np.random.uniform, low equals 1.0, high equals 2.0, and size equals tuple 2, 2. Or we could sample 2 values from a standard normal distribution with np.random.normal. And then we'll pass in loc equals 0.0, scale equals 1.0, and size equals 2. Or we could build a 3x2 array with random binomial values like np.random.binomial, and then pass in n equals 10, p equals 0.25, and size equals tuple 3, 2. And there's a whole bunch of other distributions supported by NumPy, so you can sample whatever your heart desires. Okay, so now let's see why everything I just showed you is deprecated. Let's suppose we're using NumPy version 1.1, and the current random number generator is ABC1. So when you do something like np.random.seed123, np.random.randint 3 size equals 3, under the hood, the random number generator ABC1 is responsible for making sure you get back a statistically valid sequence of random integers, and anyone else using NumPy who writes the same exact code gets back the same exact sequence. Then somebody comes along and discovers a new random number generator, DEF2, that actually does a better job of creating statistically valid random numbers. So NumPy decides to replace the ABC1 generator with the DEF2 generator. So when you upgrade to NumPy version 1.2 and run the same exact code as before, you get a different sequence of random numbers. This is an issue because 1, some people have code or documentation that might break if the random numbers they were generating suddenly change. And 2, if people can't share a reproducible example because they're on different versions of NumPy, that's really inconvenient. I mean, think of all the old examples on Stack Overflow that would instantly become non-reproducible because NumPy updated their random number generator. Another possibility is that someone comes along and creates a new random number generator, GHI3, that's way faster than DEF2, but slightly less statistically valid. Now NumPy has this problem of deciding whether to use the fast generator or the more accurate generator. The solution to this was to create a generic generator class that lets you pick the random number generator you want to use. For the sake of simplicity, I'm just going to use NumPy's default RNG method, which at the moment selects the PCG64 random number generator. And in fact, when you look at the documentation for functions like randint, that's what this note suggests. So all I have to do is say generator equals np.random.defaultRNG, and then I have the option to pass in a seed like 123. Now let's see how we can reconstruct some of the examples from earlier. So if I want to sample 3 random integers between 1 and 6 with replacement, instead of using np.random.randint, I can use generator.integers. If I want to choose 3 values between 0 and 9 with replacement, instead of using np.random.choice, I can use generator.choice. And if I want to permute the rows of foo, instead of doing np.random.permutation foo, I can do generator.permutation_foo. And this time I actually get an axis argument. So if I wanted to, I could permute the columns of foo by setting axis equals 1. And all of the distribution sampling methods we covered earlier, like uniform, normal, and binomial, are implemented as generator methods as well. In this problem, you're a relationship scientist, and you've developed a questionnaire that determines a person's love score, a real-valued number between 0 and 100. Your theory is that two people with similar love scores should make a good match. Given the love scores for 10 different people, create a matrix where element ij gives the absolute difference of the love scores for person I and person j. All right, so here's the solution that I came up with. And before we break it down, let's go ahead and do np.set_print options. We'll say line width equals 999. So here I've told NumPy not to wrap a line of text unless it exceeds 999 characters. By default, I think it wraps after 75 characters. Now in general, the set print options method is pretty handy, and if you dig through it, you might find some print options you want to change to suit your personal preference. So now let's dig into the actual logic of the solution. The trick here is really about broadcasting. If we could restructure the love scores array into a vertical column like this, in other words, a single column of a 2D array, and then subtract a row of love scores like this, the result will broadcast into a difference matrix like this. Here, the ij value in the difference matrix corresponds to the ith value in the column minus the jth value in the row. And from there, we can just use np.abs to get the absolute difference between pairs of love scores. So the question is, how do I restructure the love scores array as a column and a row? And the key there is to give love scores a new axis using np.newaxis, or alternatively the keyword none. So if I say love_scores, open square brackets, colon, comma, none, it gets a new last axis. In other words, it goes from a 10 by array to a 10 by 1 array. And if I do love_scores, square brackets, none, comma, colon, it gets a new first axis, and it goes from a 10 by array to a 1 by 10 array. So then I can just subtract these and take the absolute value to get the desired result. Also note that I actually don't need to promote this guy to a 1 by 10 array. I could just leave it as a 1D array like this, and NumPy will promote it for me. But personally, I kind of like being explicit about it because I think it makes it more obvious what's happening. You're a vindictive, hateful professor, and one of your pet peeves is when students rush through their exams. To teach them a lesson, you decide to give zeros to the first 3 students who score less than 60 in the order they turned in their exams. So given a 1D array of integers, identify the first 3 values less than 60 and replace them with 0. All right, so here's the solution that I came up with. Let's go ahead and break it down. So before I explain it, I need to rebuild my scores array. And now let's just start with this part, scores less than 60. So this is pretty straightforward. This just determines whether each score is less than 60, and it returns a boolean array. So now the guys we're interested in are the true values. Those are the people who scored less than 60. And what would be useful is if we could get the index of each true value. So NumPy has a handy function called non-zero, which returns the indices of elements that are non-zero. So if I have an array like np.array, open parens, square brackets, 0, 1, 2, 0, and I call dot non-zero, it spits back a tuple with indices for the non-zero elements. So in this case, indices 1 and 2 have non-zero elements. Actually, let me make this 3 and 4 just to make this a little bit more clear, right? So it's indices 1 and 2 have non-zero elements. So the reason it returns a tuple is if you have a multi-dimensional array, like let's say, for example, you had a 2D array, each element of the tuple would return an element that corresponds to a single dimension. So for a 2D array, the first element of the tuple would give the row indices, and the second element would give the column indices corresponding to those non-zero values. So in our case, we just have a 1D array, so we get back a tuple with one element, which looks kind of stupid, but that's why. So we can actually apply this non-zero function on this array of Boolean values because Boolean values, well, false and true are synonymous with 0 and 1. And you can use them with multiplication, division, functions like non-zero. It comes up as a super useful trick in many circumstances. So what we can do is we can say scores less than 60 dot non-zero. And this gives us a tuple where the first element has the indices of these true values. Again, true is 1, false is 0. So then if we just do square brackets 0, we can pick out that array. So now we're getting back the array of indices with true elements. And then we want to get the first 3 people, the first 3 true elements. So the first 3 people scored less than 60. So we can say square brackets :3, which means give me every element up to but excluding the third index. And now we have the indices for those people. So now we just need to say scores, square brackets, and then identify those people and give them a big fat 0. Now if I print my scores array, you can see that it updated as we wanted. Eager to make your mark on the PTA, you decide the best way to hide eggs for the upcoming Easter egg hunt is to use NumPy. You represent the field as a 10 by 10 array of zeros. Now your goal is to insert 20 random normal values at random, non-repeating locations in the grid that tell you how much candy to hide at each spot and where. Here's the solution that I came up with. Before we break it down, let me rebuild the field array. Let's start with the easy part. So we need to fill 20 eggs with a random amount of candy based on a normal distribution. So we know how to do that. We can start by building a generator, and then we can say generator dot normal size equals 20, and that gives us 20 random normal values. Now I'm going to clean this up a little bit, so I'll wrap this with np.round and round each value to 2 decimal places. And let's assign that to a variable called vals. All right, so the hard part to this challenge is really how do we map these values into unique locations in the field array? So imagine that we assign a unique value to each location in this array. So we'll say this is value 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and so on up to value 99. So then our goal is to randomly select 20 values between 0 and 99 without replacement. Well, we know how to do that. We can use the choice function for that. So we can say logs equals generator.choice, and we want to sample values between 0 and 99. So we want to sample the 100 values starting at index 0 or value 0. We want to sample 20 values, and we want to do it without replacement. Now to make this a little bit more dynamic, we can say field.size, that's the number of values in the array, and len vals. So we want the number of locations to match the number of candies that we have. And then let's go ahead and print logs. Okay, so now we've selected 20 random non-repeating locations. So now the challenge is, how do we get these candies into these locations that we've kind of just made up? Well, it turns out there's a function called ravel, which frankly I think should have been called unravel. And what it does is it takes a multi-dimensional array like this and flattens it into a one-dimensional array like this. And you could do this in different orders. By default, it uses row major order, which is exactly the system that we've described. So what we can do is we can say field.ravel, and let's just take a look at this real quick. So there's the flattened 1D array. And one thing to note is that in general, this does not return a copy of the field array, but it also doesn't modify it. This is what's called a view, and we'll talk more about that later. But basically, if I print the field array, notice that it hasn't changed. It's still a 2D array. So this is just like a temporary view that we can use. So we can say field.ravel, and then we'll pass in our lokes as indices, and we'll set those values equal to the amount of candy. So now if we print field, you can see that it mapped the candy amounts into these locations of the 2D array field. In this video, we'll see how you can use NumPy's where function as a vectorized approach to writing if-else statements. Suppose you have two 1D arrays, foo and bar, each with 2 million elements. You want to create a third array called baz, such that where bar is even, you double the corresponding value of foo, otherwise you take half the corresponding value of foo. You might be inclined to do this with a for loop like this. Here we'll set baz equal to np.zero's foo.size. Then for I in range foo.size, if baz I mod 2 equals 0, we'll set baz I equal to foo I times 2. Otherwise, we'll set baz I equal to foo I divided by 2. You probably noticed that this technique took a while to execute. The slowdown happens because for every iteration of the loop, Python has to call some lower level function in C, and then C has to give the result back to Python. This back and forth communication between Python and C is the bottleneck in our implementation. Now, NumPy is specifically designed to address this problem. Instead of going back and forth between C and Python, we want to say, hey C, here's my array and here's what I want to do with it. Now carry out the entire operation and come back to me with the result. This is called vectorization, where C operates on a batch or vector of data before giving the result back to Python. In general, if you're writing a for loop to process some NumPy array, you're doing it wrong. Going back to our example, the vectorized way to solve this problem is to use NumPy's where function. Where takes three main parameters: a Boolean array, values to use when the Boolean array is true, and values to use when the Boolean array is false. So we can solve our original problem using baz equals np.where bar mod 2 equals 0, comma, foo times 2, comma, foo divided by 2. Let's use the array equal function to make sure baz and baz really are the same. So we'll say np.array underscore equal, open parens, baz, comma, baz. And sure enough, they are equal. Now, if you're in a Jupyter or IPython notebook like this one, you can use the magic command %time it to measure the runtime of a block of code. If we do that here, you can see just how much faster the vectorized where function is compared to the Python loop. So here I'll say %time it, and you can see it takes about 2.17 seconds to run this block of code. Now let's do that here. So %time it. And by comparison, the where function takes about 57 milliseconds to run the same line of code. So you can see how much faster the vectorized where solution is than this for loop. NumPy provides a variety of math functions like sum, mean, min, max, floor, round, exp, log, and countless others. When you understand how to use one of these functions, you'll understand how to use nearly all of them. So in this video, we're going to dive into the sum function, but everything we discuss will be applicable to a bunch of other math functions. Here we have a 2D array called squee. Let's see how we can use the sum function to sum its elements. If we call np.sum squee with no other parameters, we get back 35, the sum of all elements in the array. If we set the axis parameter equal to 0, we can sum across axis 0, in other words, calculating column sums. Alternatively, we can set axis equals 1 to calculate row sums. In both of these cases, NumPy collapses our 2D array into a 1D array. But if you'd rather retain 2 dimensions, you can set keepDims equals true. Now let's see what happens if squi contains nan values. We'll start by setting the top left value of squi to nan. And let's go ahead and sum all the values in squi. In this case, NumPy returns nan because the sum function expects all values to be non-nan. In some cases, your data is going to have nan values, and you're going to want to sum them as if they were zeros. There's a few ways you can do this. So your first option is to use the where argument to exclude nans. So you could do something like np.sum squi, comma, where equals not np.isNanSqui. Here, the where argument just needs to be a boolean array that tells the sum function which values to include in the sum. Your second option is to use the nan to num function, which takes an array and replaces nan values with some other specified value, which by default is 0. So in this case, we could do np.sum, np.nan to num squi. And then your third option, which is probably my favorite, is to use the nan sum function, which works just like sum, but it treats nans as zeros. In this video, we'll see how you can use the all and any functions to identify arrays where, you guessed it, all or any of the elements match some condition. These are often used to identify rows in a 2D array that contain at least one nan value, or all nan values. So let's give that a try. Here we have a 2D array foo with some nan values scattered about. If we wanted to see which rows have at least one nan value, we can start by calling np.isNanFoo, which tells us whether each value in foo is nan, and then we can wrap that in np.any and set axis equals 1. If we assign this to a variable called mask, we can use it as a boolean index to return rows of foo with at least one nan value. Alternatively, if we wanted to see which rows of foo have all nan values, we can do the same thing with the all function. In this video, we'll see how you can use the concatenate function to combine 2 or more arrays. This function takes 2 primary arguments. The first is a sequence of arrays you want to combine, usually a tuple or a list. The second argument, axis, specifies the axis along which you want to combine the arrays. For example, if the arrays are 2-dimensional, do you want to combine their rows, axis 0, or their columns, axis 1? NumPy uses axis 0 by default. Here we'll make a 3x2 array called roux and a 2x2 array called gumbo. We can combine roux with a couple copies of itself row-wise, or column-wise. We could also combine roux and gumbo row-wise, but as you might expect, we'll get an error if we try to combine them column-wise because they don't have the same number of rows. In general, when you concatenate arrays, they must have the same exact shape, excluding the axis along which you're concatenating. In this video, we'll see how the functions hstack, vstack, and stack are a lot like the concatenate function with some subtle differences that can come in handy. Let's start by building some helper arrays. We'll make a 2x array called foo, another 2x array called bar, a 1x2 array called baz, a 1x3 array called bingo, and a 2x2 array called bongo. Now let's take a look at vstack. So vstack takes one argument, a sequence of arrays, and you could describe its algorithm in pseudocode as the following. For each array in the sequence, if the array is 1D, then promote the array to 2D by giving it a new front axis. If every array in the sequence has the same shape, then concatenate the arrays along axis 0, otherwise throw an error. Visually, you could imagine VStack as vertically stacking 1D or 2D arrays. So if we VStack foo and bar, we'll get back a 2x2 array like this. And if we VStack foo, bar, and baz, we'll get back a 3x2 array like this. And if we VStack baz and bingo, we'll get an error because their shapes don't align for VStack. Let's take a look at hstack. Hstack also takes one argument, a sequence of arrays, and you could describe its algorithm in pseudocode as the following. If every array in the sequence is 1D, then concatenate the arrays along axis 0. Else, if every array has the same shape excluding axis 1, then concatenate the arrays along axis 1. Otherwise, throw an error. Visually, you could imagine hstack as horizontally stacking 1D or 2D arrays. So if we hstack foo and bar, we'll get back a 4x array like this. If we hstack baz and bingo, we'll get back a 5x array like this. If we hstack foo and bingo, we'll get back an error because their shapes don't align for hstack. And if we hstack bingo and bongo, we'll get another error because their shapes also don't align for hstack. Lastly, stack takes two primary arguments, a sequence of arrays to combine, and axis, which tells stack to create a new axis along which to combine the arrays. In pseudocode, you could write stack's algorithm as if every array is the same shape and axis is less than or equal to the dimensionality of the arrays, then for each array, insert a new axis where specified, and then concatenate the arrays along the new axis. Otherwise, throw an error. Depending on how you set the axis parameter, stack can combine 1D arrays vertically or horizontally. So let's see what happens if we stack foo and bar with axis equals 0. Remember the algorithm, foo and bar each get a new axis 0, promoting them from 2x arrays to 1x2 arrays, and then they're stacked along that new axis, so row-wise, resulting in a new 2x2 array. If we stack them along axis 1, they go from 2x arrays to 2x1 arrays, and then get stacked column-wise into a new 2x2 array. If we try to stack foo and bar with axis equals 2, we'll get an out-of-bounds error. Remember, the new axis must be in the range of the array's existing dimensionality. You can also use the axis equals -1 shortcut to make the new axis the last axis. For foo and bar, it'd be like using axis equals 1. In this video, we'll see how you can use NumPy's sort function to sort the elements of an array. Sort takes three primary parameters: the array you want to sort, the axis along which to sort, the default -1 sorts along the last axis, and the kind of sort you want NumPy to implement. By default, NumPy implements quicksort. For example, here we make a 1D array foo, and then sort it in ascending order. Note that this creates a copy of foo before it sorts its elements, and the original array remains unchanged. If you want to sort the values of foo in place, use the .sort method of the array object. In other words, if you do foo.sort, this time foo updates with its values in sorted order. If you have an array with nan values like this one, sort pushes them to the end of the array. Unfortunately, NumPy doesn't have an easy, direct way of sorting arrays in descending order. However, with a bit of thought, we can cook something up. So two methods really stand out. The first is to sort the array in ascending order and then reverse the result. The second is to negate the array's values, sort those in ascending order, and then negate that result. The main difference between these techniques is that the first method pushes nans to the front of the array, and the second method pushes nans to the back. Also, the second method won't work on strings since you can't negate a string. What if you wanted to sort a multidimensional array like this? In this case, you can use the axis parameter of the sort function to specify which axis to sort along. For example, if we do np.sort boo, axis equals 0, it sorts boo along axis 0. In other words, it sorts each column of boo. And if we do np.sort boo, axis equals 1, it sorts boo along axis 1. In other words, it sorts each row of boo. We can also set axis equals -1 to tell NumPy to sort the last axis of an array. In this case, it'd be like sorting boo along axis 1. Cool. But what if we wanted to sort the rows of boo according to, say, the values in the first column? If we had something to give us the array 1, 0, 2, we could pop that into the row index and get back our desired sorted array. The tool we're looking for is argsort. Argsort works just like sort, except it returns an array of indices indicating the position each value of the array would map to in the sorted case. For example, if you had the array 3, 0, 10, 5, and you called argsort on it, you'd get back the array 1, 0, 3, 2, because the smallest element is at index 1, the second smallest element is at index 0, and so on. If you use this array to index the original array, you get back a sorted array just as if you called np.sort. So if you wanted to sort a 2D array's rows based on a certain column, you just have to call argsort on that column's values and then use that result to select rows from the original array. Looking back at our 2D array boo, we could sort its rows by the first column ascending like this. This brings up an important question. If our array has repeated values, like 55 in this case, how do we guarantee that sorting them won't alter the order they appear in the original array? For example, this matrix and this matrix are both valid sorts of boo along its first column, but only the first matrix doesn't mix up the order of the 55s. This is what's known as a stable sorting algorithm. By default, np.sort and np.argsort don't use a stable sort algorithm, but you can force it to by setting the kind parameter equal to stable. In this video, we'll see how you can use the unique function to get the unique elements of an array. It's pretty simple to use. If you have an array called gar, then unique gar gives you the unique elements. Simple enough, although you may have noticed that the order in which the elements occurred in the original array is different than the output. In the original array, B occurred first, but in the output, A occurs first. That's because unique returns the unique elements in sorted order. Let's try that again, but this time we'll call unique with return index equals true. With return index set to true, NumPy gives us a tuple containing the unique elements array and a corresponding array that tells us the index at which each element first occurred in the original array. For example, A first occurred at index 2 in the original array, B first occurred at index 0, and so on. This is useful if you want to reorder the unique elements in the same order they occurred in the original array. To do this, argsort the index array and use that to sort the unique array. Another sweet feature of unique is that you can tell NumPy to return the count of each element. To do this, just set return counts equal to true. You're given a 10x2 array of floats where each row represents a movie. The first column represents the movie's rating, and the second column represents the director's rating. Your goal is to create a third column to represent the overall rating. The overall rating is equal to the movie rating if it exists, otherwise it's the director's rating. Okay, I came up with two solutions to this problem, so let's go ahead and take a look at the first solution. Let's break it down. So here we use the where function, and we basically say where the first column of the ratings array is nan, go ahead and use the value given in the second column. Otherwise, use the value given by the first column. And we assign that to a variable called x. So if I just print x here, you can see this gives us the values that we want to insert into the third column. So then the challenge is, how do we put these values into the ratings array? And for that, we can use the insert function. So we say np.insert, and we pass in the array we want to insert into, the values that we want to insert. So in this case, x, the array we just created, the axis, so we want to insert it as a column, so axis equals 1, and then the location, so obj equals 2 means we want to insert these values at index 2 of axis 1. In other words, the third column of the array. And then we assign that to a variable called result. So note that the insert function doesn't actually modify the ratings array. If I print ratings, you can see it hasn't changed. So we return this copy with the new column inserted into a variable called result. Here's the second solution that I came up with. So it starts out just like the first solution, where we define x as the new values that we want to insert into the last column. And then we use the hstack function to horizontally stack the ratings array with x. Now the trick here is the ratings array is a two-dimensional array, so we need x to become a two-dimensional array to make it compatible for stacking, and we can do that with x square brackets colon comma none, where we give it a new last axis. If you want to see what that looks like, it basically looks like this, and that's what makes it compatible for stacking with this ratings array. And then the result is what you'd expect. 10 fish occupy a 5 by 5 by 5 grid of water. Each fish decides to move to a new ijk location given by the matrix below. If multiple fish end up occupying the same cell, the biggest fish eats the smaller fish. Determine which fish will survive. All right, here's the solution that I came up with. Let's break it down. So imagine we assign an ID to each fish, where the IDs are simply 0, 1, 2, 3, 4, and all the way up to 9. Then we can start by sorting the IDs based on weight from heaviest to lightest. So if we do np.argsort weights, we'll get back the IDs of fish sorted from lightest to heaviest. So if we reverse that with square brackets colon colon -1, we'll get back the IDs from heaviest to lightest, and then we can assign that to a variable called sorted fish. Now, if we index the lokes array using sorted fish, it'll reorder the rows of lokes based on the weight of each fish. The heaviest fish has its new ijk location listed first, the second heaviest fish has its location listed second, and so on. Now, notice the duplicate locations here, like the zeros row here, the zeros row here, and the zeros row here. Well, the fish that's going to survive is the one that corresponds to this row, because it's the heaviest fish. So all these three fish are going to collide, but this guy's going to survive because the heaviest fish are listed first in this array. So what we want to do is we want to get the index of the first occurrence of each unique value in this array. And we can do that with np.unique, where we set return index equal to true. So we'll say uniques first indexes equal np.unique, and then we'll pass in lokes square bracket sorted fish. We'll set axis equals 0 because we want unique values across axis 0, in other words, unique rows. And we set return index equals true to get the first index of each unique value. And then we'll go ahead and print uniques, and we can print first indexes. So now if we say sorted fish, square brackets, first indexes, we'll get the ID of each surviving fish. You own a taco truck that's open 24/7, and you manage 5 employees who run it. Employees work solo 8-hour shifts. You decide the best way to set their schedule for the upcoming week is to create a bunch of random schedules and select the one that looks best. You build a 1000 by 21 array of random employee IDs where element ij gives the employee ID working shift J for schedule I. A schedule is valid as long as no employee works 2 consecutive shifts. Get the row index of all valid schedules. All right, let's see the solution that I came up with. And let's go ahead and break it down. So we want to compare adjacent values in each row and make sure that no 2 neighbors are the same. So for example, here you can see employee ID 0 works these 2 consecutive shifts for the first schedule. So this is going to be an invalid schedule. And there's 21 columns, which means that we want to compare 20 pairs of adjacent elements for each row. Now we can do that by picking out the first 20 columns and comparing that to the last 20 columns. In other words, the matrix that's offset 1 column to the right. So to do that, well, to pick out the first 20 columns, we can say schedules square brackets colon, comma, colon -1, which means pick out every row and every column up to but excluding the last column, and we'll check for not equals. So then we pick out the last 20 columns, and we can do that by saying square brackets colon comma 1 colon, which means give me every row, but only the columns starting from index 1 up until the end. So when we run this, we get a big Boolean array. It's a 1000 by 20 Boolean array. And then the true values are good. The true values mean that the adjacent employee IDs are not the same. So we want to identify rows where every value in the row is true. That means it's a good schedule. So what we'll do is we'll use the all function, and we'll say np.all, and then we'll pass in what we just built. And we want to do it for each row. So we'll say axis equals 1 because we want to check that the values are all the same or all true across axis 1. So when we run this, what we get is we get a big 1D Boolean array. It's a 1000 by array of Boolean values. So then the good schedules are going to be identified by true values in this array. And if you remember, false and true are synonymous with 0 and 1. So we can actually use the np.non-zero function to pick out all non-zero values, which again, for a Boolean array, it means it's picking out the true values or the indices of true values. So we'll say np.non-zero. And the non-zero function actually returns a tuple where it has 1 element for each dimension in the given array. In this case, we only passed it in a 1-dimensional array, so we want to pick out the first element of the result, and that'll give us the indices of valid schedules. Earlier in the course, we discussed array indexing techniques, but the truth is I glossed over a lot of gritty details and complex scenarios. In this video, we'll take a deeper dive into how array indexing works. Let's start by setting up a 3x2x4 array of integers called foo. What do you think the result of foo open square brackets colon colon 0 will return? Recall the mental model for interpreting an n-dimensional array. If you have a 1D array, think of a single row of values. If you have a 2D array, think of a matrix. If you have a 3D array, think of a row of matrices. If you have a 4D array, think of a matrix of matrices, and so on. In this case, we can think of foo as a row of matrices where element ijk corresponds to the ith matrix, the jth row, and the kth column. So when we do foo square brackets : 0, we're requesting every matrix, every row, column 0. And so we get back this subarray. The thing that might be surprising in this case is that we started with a 3-dimensional array and we got back a 2-dimensional array. Now, it kind of makes sense because we only picked out one column from foo, so there's really no need for NumPy to retain that third dimension. But as soon as we select more than one column, for example like this, we'll get back an array with 3 dimensions. Now, I'll explain later why that is, but let's take a look at a few more examples first. What do you think we'll get back if we do a subset like this? Let's reorganize those index arrays to make this a little more clear. Did you come up with this output array? So this is a really critical thing to understand. When every dimension is indexed with an array, and each of those arrays is the same shape, the output array will be the same shape as the index arrays. In this case, each of our index arrays is a 3x2 matrix, so we know our result will also be a 3x2 matrix. Now, to understand the values in the result, you can imagine zipping our 3 index matrices into a matrix of 3-element tuples, like this one, where each tuple gives the location of the corresponding output element. Just to drive this point home, take a look at this example where we use 4-dimensional index arrays to extract values from our 3-dimensional array, foo, and we get back a 4-dimensional array. So again, the shape of the output is dependent on the shape of the index arrays, not the shape of the array you're indexing into. Okay, so we've considered the case where every dimension has an index array, and each of the index arrays is the same shape. Now, what if every dimension has an index array, but the index arrays have different shapes? So for example, what do you think the output of this will be? Did you get this? In cases like this, NumPy broadcasts the index arrays so that, in essence, we get back to the previous case where each index array is the same shape. In this case, we have a 2x array, another 2x array, and a 3x1 array, so those are going to broadcast into 3x2 arrays like this. And now subsetting foo with equivalently shaped index arrays is straightforward based on what we already covered. Lastly, we consider the case where our array has slice indexers, i.e. colons. For example, what do you think the result of this index will be? Did you come up with this 3x4x2 array? So what's going on here? The mental goal to figuring these things out is to build fully expanded, same-shaped index arrays for each dimension, and we can do that as follows. So first, we broadcast all index arrays, and then for each slicer, we copy each index array n times along a new last axis, where n equals the size of the current slicer's dimension, and then we represent the current slicer with an index array. Alright, so let's walk through that last example. We start by broadcasting our index arrays. In this case, we have a 4x array in the I index and a 3x1 array in the k index. So those broadcast to the following 3x4 arrays. Now let's make up an index array for j, the same shape as these guys, and fill it with zeros. These index arrays almost give us what we want. The problem is that j is always picking out the first row of foo, but we want it to span every row of foo. In other words, given some I-k pair, we want to retrieve every possible j. And since foo has 2 rows, you can imagine that we replace each 0 and j with an array of every possible row index. So in this case, we replace each 0 with the array 0, 1. And then we need to expand I and k accordingly by copying each of their elements twice, like this. And we can reorganize these arrays like this. So our expanded index arrays all have the same shape, 3x4x2, and indeed that's the same shape as our output. Note that the slicer, i.e. the colon we used in this example, is a full slice, but we could use fancier slices like : 2, which gets every second element, or :3, :-1, which gets the first 3 elements in backwards order. And with these fancier slices, I hope it's clear how you tweak our methodology to determine a resulting array. Another thing to note is that we can leave out trailing indexes, in which case NumPy assumes we want all the values from those excluded dimensions. For example, if we do foo square brackets and then pass in the list 0, 1 with nothing else, it's like saying, give me the complete first and second matrices in foo, and it'd be equivalent to writing foo square brackets list 0, 1, :::. Now let's circle back to an earlier question. When we do foo square brackets : 0, why do we get back a 2-dimensional array when we started with a 3-dimensional array? Well, let's follow our algorithm for determining the output shape. We start by broadcasting all of the index arrays. Now in this case there's only one, so we don't have to do any broadcasting. But what's the shape of a scalar like 0? It's actually empty or 0-dimensional. You can see this by calling empty.array 0.shape. So we have an empty dimensional index. Then we concatenate that with the size of each dimension with a slice. So we end up with a 3x2 result. In this video, we'll shed some light on when array indexing produces a view and when it produces a copy. Say we have this 2D array, squid, and we index the array like this, where we use slices to pick out every row in the first 2 columns. Instead of using a slice for the column subset, we could accomplish the same thing with an index array like this. On the surface, these techniques seem to produce the same result, but there's a subtle and really important difference. Ward is actually a view of the squid array, whereas sponge is a copy of the squid array. Well, at least the portion we subsetted. You can see this a couple different ways. If I set the first element of sponge to 100, obviously sponge gets modified, but squid and ward stay the same, as you'd expect. But if I set the first element of ward to 100, not only does it modify ward, but it also changes squid. This can lead to some nasty, undetected bugs if you're not careful. Another way you can see this is if you look at the memory address of the beginning of each array. So for example, if you do squid.__array_interface__, and then the same thing for ward and sponge, you can see where squid and ward have the same memory address, unlike sponge. But that memory address points to the beginning of each array, so this method only identifies a view if it includes the first element of the original array. A better technique is to use NumPy's shares memory function, which is specifically designed to tell if 2 arrays have overlapping memory. Here you can see it in action. In general, when you subset an array using nothing but slices, you're going to get back a view of the original array. You can force NumPy to copy the data by appending .copy to the end of your statement, like this. And when you subset an array using at least one index array, NumPy will automatically copy the data so you don't have to worry about overwriting the original array. You manage a local department for the census responsible for measuring the population of each block in the city where you live. Even though you could do it yourself, for each of the last 5 years, you've tasked this job to your subordinate Jim. What Jim gives you each year is a 2x4 array of his population estimates, where each element of the array represents a city block. After 5 years, you have a 5x2x4 array of population estimates called Jim, where ijk represents Jim's population estimate for block jk in year I. The thing is, you don't fully trust Jim's estimates because you see him spending an ungodly amount of time on Facebook. So each year, you go behind his back and measure the population of 2 city blocks. After 5 years, you have the following data. Blocks, a 5 by 2 by 2 array indicating which blocks you measured each year, where ij gives the coordinates for the jth block you measured in year I, and pops, a corresponding 5 by 2 array with the population you measured for the jth block in year I. How many times was Jim's estimate at least 10% higher or lower than your estimate? So to make this more clear, these are Jim's population estimates. And so, for example, these are his estimates in the first year. These are his estimates in the second year, third year, and so on. And blocks and pops corresponds to your estimates. So for the first year, you measured these two city blocks, block 02 and block 13, and the population you came up with for this first block was 100. So your estimate of 100 corresponds to block 02, which corresponds to Jim's estimate of 92. And again, your goal is to determine how many times Jim's estimate was at least 10% higher or lower than your estimate. All right, here's the solution that I came up with. So let's go ahead and break it down. Now, our initial goal is to build a 5 by 2 array of Jim's estimates that correspond to our 5 by 2 array of estimates. But before we do that, let's reimagine the Jim array as a row of matrices, and we'll do the same thing with the blocks array. So if I want to subset the Jim array and get back a 5 by 2 array, I can do that by using 5 by 2 index arrays for the I, j, and k dimensions. So let's set up that framework. So here I'll say I equals, and then I'll pass in a list, and let's just initialize it with all of zeros. So we'll do 0, 0, and we'll do 5 copies of that. And then we'll do the same thing for j and k. So these are index arrays that we're going to pass into the Jim array like this to pick out the elements that we want to fetch. So I here represents the year of the population estimates. So looking back at our pops array, well, the first row should just be year 0, and then we're going to pick out year 1, year 2, year 3, and year 4. Now, the j index array here is going to correspond to the first column of each nested matrix in the blocks array. So the values we want for the first year are going to be 0 and 1. So we'll say 0, 1, and then in the second year, it's going to be 1, 0. The third year will be 0, 1, and then 1, 0 again, and then 0, 1. And then the k index is going to correspond to the second column of each nested matrix in the blocks array. So in this case, we're going to pass in 2, 3, two, 0, 0, 2, 1, 3, and 1, 0. Okay, so if we run this, we'll get back the corresponding population estimates that Jim got, which correspond to our population estimates. So how do we make this a little bit more dynamic? Well, let's focus on the j index array here. So what we're picking out with the j is we're picking out every matrix in the blocks array, every row of each matrix, but only the values in column 0. So we can replace this sort of hard-coded array with blocks, square brackets, colon, comma, 0. And then the k-index array is nearly identical, except we're picking out the values in column 1. So that leaves us with the I index array. Now notice the duplicate columns here. So we can actually get rid of this second column. And what will happen internally when we do this index here is that I will broadcast to match the shape of J and K. Now, this array here we can represent with np.arange, open parenthesis 5, square brackets, colon, comma, none. So remember, np.arange is just a 1D array, 0, 1, 2, 3, 4, and then square brackets, colon, comma, none just promotes that from a 5 by array to a 5 by 1 array. Okay, so once again, we have Jim's estimates. Let's go ahead and assign that to a variable called Jim_pops. So from here, the rest is fairly straightforward. If we do pops minus Jim pops, we get the difference between our estimates and Jim's estimates. If we wrap that in np.abs, we get the absolute differences. We divide by pops and we get the percent differences, or absolute percent differences. We'll check greater than or equal to 0.10 to determine which of them is at least 10% different. And then we can sum the true elements with np.sum and determine that 2 of Jim's estimates are at least 10% different than our own estimates. Given a 10 by 10 by 10 array of zeros, set ijk equal to 1 if all of the following hold true. I is odd, j is even, and k is prime. In other words, set these elements to 1. Okay, here's the solution that I came up with. Let's break it down. So the I indices that we're interested in are going to be the odd indices. So those are going to be 1, 3, 5, 7, and 9. J is going to be the even indices, 0, 2, 4, 6, and 8. And K will be the prime indices. So those will be 2, 3, 5, and 7. Now, the specific elements that we want are actually going to be the Cartesian product of these 3 arrays. So in other words, the combination of these 3. So 1, 0, 2, 1, 0, 3, 1, 0, 5, and so on. In total, it's going to be 5 times 5 times 4, so 100 elements that we want to update to 1. So if we try to do something like Chewy, square brackets, I, comma, j, comma, k equals 1, this actually will give us an error, and it's not at all what we want. What this is attempting to do is it's attempting to set element 1, 0, 2 as 1, then 3, 2, 3 as 1, 5, 4, 5, 7, 6, 7, and then lastly element 9, 8, and then this is missing a k index, so that's where you get the error. But besides the fact that it errors, it's really trying to just update 5 values instead of 100 values. So what we want, like I said, is going to be the Cartesian product of these guys. Now, one way you can do that is with broadcasting. So if I do I square brackets colon comma none, this turns my 5 by array into a 5 by 1 by 1 array. And then if I do j square brackets none colon none, this turns into a 1 by 5 by 1 array, and k square brackets none comma colon becomes a 1 by 1 by 4 array. So NumPy will broadcast these index arrays into the following 5 by 5 by 4 index arrays. And you can imagine that they get zipped together into the following tuples, which pick out the exact elements that we want to update and set equal to 1. Now, there's a shorthand way to do this, and that's with the function np.ix_. And so if I say np.ix underscore and I pass in a sequence of 1D arrays like I, j, and k, it returns what's called an open mesh, which is exactly what we've done here. So then all I have to do is say chewy square brackets np.ix underscore ijk, close square brackets, and set that equal to 1. And this statement here is equivalent to this statement here. So that's just a shorthand way to subset an array when you have 1D arrays and you want to sort of get the Cartesian product of these to select out specific elements. You're preparing for a game show where you play the following game. You're faced with 4 doors. Behind one door is cash money, and behind the other 3 doors is a steaming pile of broccoli. If you pick the door with money, you get the option to play again at the risk of losing the money you've collected thus far. If you keep winning, you can play a maximum of 3 rounds before the game show host kicks you off his show. You have some strategy ideas you'd like to evaluate before you go on the show. So you hired an unpaid intern to scour through historic recordings of the show and log data on where prizes were located and the value of each prize. Your intern gets back to you with the following matrices. Prize doors, a 5x3 array where element ij gives the door hiding the prize in the jth round of the ith game, and prizes, a 5x3 array where element ij gives the prize amount in round j of the ith game. Build a 5x3x4 matrix where ijk represents the prize behind door k of round j of game I. Okay, here's the solution that I came up with. Let's go ahead and break it down. So the first thing I do is initialize an array called answer. So answer is a 5x3x4 array of zeros, where this corresponds to the fact that we have 5 games. Each game has 3 rounds, and each round has 4 doors. And these values are like the cash prizes behind each door. So we want to update the values that we know have cash prizes behind them. And that's going to be given by the prize doors array and the prizes array. So let's start by sort of looking at the prize doors array. Now, these doors are actually indices. And so, for example, prize door 1, this means that in the first game, in the first round, the prize was behind door number 1. And that's going to correspond to the first game, first round, door number 1 is going to be this guy. So we'll want to update this value with the cash prize 100. So if we think about these doors where the cash prizes were hidden, well, this is game 0, round 0. This one represents game 0, round 1, game 0, round 2, game 1, round 0, game 1, round 1, game 1, round 2, and so on. So we can build corresponding 5x3 index arrays for the game indices and the round indices. So let's go ahead and do that. So if we say game indexes, and we'll set this as, again, we want to make it a 5x3 array. So 1, 2, 3, 4, 5. And so the games we're interested in are going to be 0, 0, 0, then 1, 1, 1, 2, 2, 2, 3, 3, 3, and 4, 4, 4. And then we can do nearly the same thing for the round indices. So the rounds in this case are going to be 0, 1, 2, 0, 1, 2, 0, 1, 2, 0, 1, 2, and 0, 1, 2. And again, I'm building these indices so that they sort of line up with the prize doors array that we already have. So now what we can do is we can say, well, answer square brackets, and we'll pass in our 3 index arrays. So game indexes, round indexes, and prize doors. And we set that equal to the corresponding prizes. So this actually gives us the solution. We're just not satisfied because it's hard-coded. So how do we make these arrays a little bit more dynamic? And we can do that with broadcasting if we set up the appropriate row or matrix and row indices. So np.arrange 5 square brackets colon comma none is going to give us this array here. So it's a 5 by 1 array. And then np.arrange 3 square brackets none comma colon is going to give us this 1 by 3 array. So these 2 arrays, when we pipe that into the square brackets here, they're actually going to broadcast, and this column is going to get copied 3 times, and this row is going to get copied 5 times. So they're going to be identical to the game indexes and round index arrays that we set up earlier. But this way it's a little bit more dynamic and easier. So putting it all together gives us my original solution. Given peanut, a 4 by 5 array of zeros, and butter, a 5-element 1D array of indices, fill the rows of peanut with 1s starting from the column indices given by butter. So for example, in the first row of peanut, you're going to start at column index 3. That's going to be here. And you're going to replace these zeros with 1s. In the second row, you're going to start at column index 0. So you're going to replace the entire row with 1s. In the third row, you're going to start at index 4. So you're just going to replace this guy with a 1. And then the last row, you're going to start at column index 1. And you want to replace these 4 zeros with 1s. Okay, here's the solution that I came up with. Let's break it down. So to start, we're going to build 2 arrays that match the shape of peanut. So the first array I'm going to build is called col indexes, and I'll say that equals np.array, open parens, open square brackets. And then I want to get the corresponding column index for each value in peanut. So the corresponding column indices in row 1 are going to be 0, 1, 2, 3, and 4. And then of course they're going to be the same thing for each row after that. So then I want to build another array, a 4 by 5 array, that gives the corresponding values from butter that we want to associate with each value in peanut. So I'll say butter expanded equals np.array, open parens, open square brackets. And so in the first row, we want to use the value 3. So I'll just say 3, 3, 3, 3, 3. And in the second row, we're going to use the value 0. So I'll do the same thing. I'll just repeat the value 0 5 times. Third row is going to get the value 4. Fourth row is going to get the value 1. Okay, so now if I make the comparison and I say butter expanded is less than or equal to col indexes, I get back a 4 by 5 Boolean array where the true values tell me if the column index is greater than or equal to the corresponding value from butter. And these are exactly the values that we want to overwrite with 1s. So for example, in the first row, we want to overwrite these zeros with 1s because they occur at column index 3 and 4. And so you can see that's why these 2 values are true while these 3 values are false. So we could use this Boolean array to subset and make a replacement in the peanut array. But an easy trick that we can do here is just convert the Boolean array to integers, or actually floats, basically zeros and ones. So we'll say this dot as type, open parens, quotes, and the reason I'm going to use floats here is to match our input type. So you can see the decimals indicating that peanut is an array of floats. So I'll say open quotes float 64. And this gives me the desired output. Now, what we want to clean up is this array and this array. We want to make these a little bit more dynamic. So let's suppose for a second that butter expanded. Well, there's a lot of repetition here. So let's just make this guy a 4-row by 1-column array like this. And you can kind of see the repetition here as well. So we'll reduce this to a 1-row by 5-column array like this. And I'm going to go ahead and insert a new cell here. And so now if we do butter expanded is less than or equal to col indexes, the result of this actually broadcasts to the exact Boolean array that we wanted. So how do we build these arrays a little bit more dynamically? Well, butter expanded. Oh, and let me back up a second. Col indexes here is a 1-row by 5-column array. It's a 2-dimensional array. It actually doesn't even need to be 2-dimensional as long as butter expanded is 2-dimensional. If this guy is 1-dimensional, that's good enough for the broadcasting to work as we want it to. So instead of doing this, we could simply replace this with np.arange and then the number of columns in the peanut array. So we'll say peanut.shape square brackets 1. And let's go ahead and print col indexes. And then here, well, this comes from the butter array. So what we'll do here is we'll say butter open square brackets colon comma none. And this reshapes the butter array into a 4-row by 1-column array. And then we just kind of put those pieces together to get this statement here, which gives us the result. In this video, we'll see how you can use the asStrided function to create complex views of an existing array. Let's start by creating a 2D array with 8 integers called foo. If you remember, earlier on in the course, we talked about how arrays are stored in contiguous, fixed-size memory blocks. In this case, foo would be stored in memory like this. Since foo is comprised of 64-bit integers, each block of memory is 64 bits. Alternatively stated, each block of memory is 8 bytes because there's 8 bits in a byte. So let's say we're here at the beginning of the array. If we want to get to the third element, we know we need to jump across 16 bytes of data. Now, let's say we're back at the beginning of the array and we want to get to the element at index 1, 1. In this case, we can do some basic math to figure out that we need to jump across 32 bytes to get to the second row, and then another 8 bytes to get to the second element in the second row. This is exactly what the strides attribute of a NumPy array tells us. For example, foo.strides returns the tuple 32, 8, which means to get to the next row, you need to jump across 32 bytes, and to get to the next column, you need to jump across 8 bytes. Here's the cool part. With np.lib.stridetricks.asStrided, you can create a new view of an existing array by modifying its strides, but not copying or modifying its data. For example, if we wanted to build a view of foo that looks like this, we can do bar equals np.lib.stridetricks.asStrided, x equals foo, shape equals 3 by 4, and strides equals 16 by 8. This works because we define a 3x4 array that's based on the data in foo, but in this array, we tell NumPy to jump across 16 bytes to get to the next row and 8 bytes to get to the next column. For example, if we request the element at index 1, 0, NumPy starts at the beginning of the array and then jumps across 1 row and 0 columns, so 16 bytes plus 0 bytes, landing here, and reads off the element 30. To get to index 1, 3, NumPy jumps across 1 row and 3 columns, so 16 bytes plus 24 bytes, landing here, and reads off element 60. Now, it's really important to note that bar is a view of foo. So if we modify bar, we'll also be modifying foo. For example, if we do bar square brackets 1, 0 equals 999, and then we print foo, notice that foo gets modified even though we changed bar. But not only that, if we print bar, you can see that element 1, 0 and element 0, 2 changed. That's because they both point to the same block of memory. If you use this function, you need to be really careful that your strides make sense, and that they don't spill outside the memory bounds of the original array. If you make your strides too big, you could end up pointing to memory that's used by a completely different variable, and you could end up crashing or corrupting your program. That's why the docs for as strided have this big red box that says warning. This function has to be used with extreme care. In this video, we'll see how you can calculate Einstein sums with the einsum function to quickly and efficiently multiply and sum arrays. Let's start by looking at a simple example. Here we have 1D arrays A and B, each with 4 elements. If we calculate the einsum of I, j goes to I, A, B, we get back the array 0, 22, 44, 66. So what the hell just happened? In pseudocode, you could describe what just happened as the following. Initialize output as an array of zeros the same size as A. For each I, for each j, output I plus equals AI times bj. So the first parameter of einsum is the subscript string. Assuming we're operating on 2 arrays A and B, it always has the form subscripts for A's axes, comma subscripts for B's axes, arrow subscripts for output axes. In this case, A has 1 dimension, so we give it the letter I. B has 1 dimension, so we give it the letter J. And by using the letter I for the output array, we're saying the output array has 1 dimension and it's the same length as A. In other words, element AI will always feed into a corresponding output I. Let's see some more examples, and I think things will start to soak in. If we do einsum I, j arrow nothing, A, B, we get back 132. We could rewrite this process in pseudocode as initialize output equal to 0. For each I, for each j, output plus equals AI times bj. Since there's no letters to the right of the arrow in the subscript string, that means our output will have 0 dimensions. In other words, our output will be a scalar. And like before, we iterate over each I in A and each j in B, adding AI times bj to the sum. What if we do einsum z, z goes to z? In this case, the pseudocode would be initialize output as an array of zeros the same size as A and B. For each z, output z plus equals az times bz. So this example is equivalent to doing the element-wise product A times B. How about this one? S, t goes to st. In this case, we get back a 4x4 array, and you could write the pseudocode for the process as initialize output as a 4x4 array of zeros. For each s, for each t, output st plus equals as times bt. Einsum really starts to shine in 2 dimensions. Let's make 2x2 arrays C and D. If we do an einsum like ij, ji goes to nothing, we get back 37. Before we write out the pseudocode for this one, let's dissect the subscript string and what it tells us. The bit before the first comma is ij. This tells us the first array we're operating on has exactly 2 dimensions. The bit after the comma is ji. This tells us the second array we're operating on also has exactly 2 dimensions. Now also, the length of its first dimension matches the length of the first array's second dimension, since they both use subscript j, and the length of its second dimension matches the length of the first array's first dimension, since they both use subscript I. The bit after the arrow is empty, so we know the output will have 0 dimensions and thus will be a scalar. Now we can write the pseudocode as initialize output equal to 0. For each I, for each j, output plus equals Cij times Dji. Notice that on the surface, this particular Einstein sum is equivalent to doing np.sum C times D transpose. The difference is that einsum only visits each element once, whereas sum C times D transpose visits each element twice. First when it does the multiplication, and second when it does the sum. More importantly though, sum C times D transpose creates a temporary array that takes up memory before it gets summed into a scalar. Einsum avoids this memory consumption, which if you're dealing with big arrays can make a significant difference. Given a 1D array of integers, one-hot encode it into a 2D array. In other words, take this array called yo and use it to build an array like this. Alright, I came up with 2 solutions to this problem. So here is my first solution. And let's go ahead and break it down. So the first thing I do is I set num classes equals np.max yo plus 1. So in this case, let me go ahead and print this. The max value of yo is 3. So we assume that there are 4 classes, specifically 0, 1, 2, and 3. Then the second thing we do is we use this function called np.i, which creates a square matrix of zeros with ones along the diagonal. So for example, if we say np.i 8, then we get an 8 by 8 matrix of zeros with ones along the diagonal. So we use this function and we pass in the value num classes. So in this case, we get a 4 by 4 array of zeros with ones along the diagonal. And you can think of each row of this matrix as representing the one-hot encoded values of each of the categories or each of the classes. So for example, the first row here, it's the one-hot encoded representation of class 0. The second row is the one-hot encoded representation of class 1, and so on. So what we want to do is we want to pick out the rows from this matrix based on the values given by yo. So we just say np.i num classes square brackets yo, and that gives us our desired result. Okay, here's my second solution. So the strategy here is to initialize an array of zeros and then fill it with ones in the correct locations. So in this case, the values of yo correspond to the columns in the output, and the indices of yo 0, 1, 2, and 3 correspond to the rows of the output. So we know we need to initialize an array of zeros that is num cases by num classes in shape, where num cases is just the length of yo, and num classes is the max value of yo plus 1, so 4. So our initial array of zeros looks like this. And then if we just think about the first couple of values of yo, so this 3 means that in the first row, we want to replace the value at index 3, so this guy, with a 1. This 1 means the value in the second row, index 1, we want to replace with a 1. Here, the 0 means the value in row 3, index 0, we want to replace with a 1, so this guy. So the way we can sort of write this out is we can say result square brackets, and then what we want is we want the array 0, 1, 2, 3, and then the values in yo. We want to set those equal to 1. And then, of course, we can make this a little bit more dynamic by saying np.arange num cases. And then if we print the result, you can see we get our desired solution. Your job is to monitor the rainfall in a region that you've broken into a 3x4 grid. Every time a storm comes, if a cell in the grid gets rain, you record it. At the end of a month, you have the following 2 arrays of data. Rain locations, a 7x2 array representing the location of recorded rainfall, and rain amounts, a 7-element 1D array representing the amount of rainfall in each corresponding location. Build a 3x4 array representing the total accumulated rainfall in each cell of the grid. Oh, and don't use a for loop. Okay, here's my solution. Let's go ahead and break it down. So the first thing we do is we initialize a 3x4 array of zeros, which we'll call rainfall. And basically this array is going to store our result. So what you might be inclined to do at this point is something like the following. So you might say rainfall square brackets, rain underscore locations, square brackets, colon, comma, 0, rain underscore locations, square brackets, colon, comma, 1, and you might say plus equals rain amounts. And what you're trying to do here is you're saying, okay, in the rainfall array, we want to update the values at indices. Well, rainfall locations, square brackets, colon, comma, 0, these are going to be the row indices of the values you want to update. Rain location, square brackets, colon, comma, 1 picks out the column indices of the values you want to update. And then plus equals rain amounts is going to cumulatively add the rain amounts that correspond to those locations. Now, the problem is this doesn't work. And where it fails specifically is the elements of rain locations that are repeated. So for example, index 2, 3 is repeated 3 times. And if we look at that location, which is this guy, the amount of rainfall in this result is actually equal to the last rain amount in that location. Another example would be element 1, 1, which is repeated twice. So this amount of rainfall that we ended up with is 0.4. I'm sorry, it's actually 2.0. Well, that's the last amount of rainfall that it got, but it actually received other earlier rainfall. So this plus equals, assignment or update statement doesn't work like you might think it does. So NumPy's solution to this problem is the .at method, which exists for all unary functions. So in this case, what we can do, the way we can modify this, is we can say np.add@, and then we pass in the array that we want to update. Let me go ahead and rebuild this rainfall array. So the array we want to update is the rainfall array. Then we pass in the indices where we want to update it. So in this case, we give it a tuple of row indices and corresponding column indices, and then the corresponding amounts that we want to add. So rain amounts. And when we run this, now you can see that this function works as we desired. After a series of poor life choices, you find yourself managing a recreational table tennis league. There are 10 participants, and in an effort to make the first round of matchups as exciting as possible, you develop a model that predicts the score difference for every possible pair of players. That is, you produce a 10 by 10 matrix where ij represents your prediction for player i's score, minus player J's score if they were to compete. Given this matrix, determine the best matchups for round 1, the matchups that minimize the sum of squared point differentials. Okay, here's the solution that I came up with. And it's pretty long, but let's go ahead and break it down. So one way we can approach this problem is by thinking about every possible schedule. So every possible schedule is just going to be every set of possible matchups between players. And just to give you an idea of what these might look like, obviously there's going to be many more than this, but an example schedule would be player 0 versus player 1, 2 versus 3, 4 versus 5, and so on. So if we imagine every possible schedule, there's going to be quite a few of these. And the question really is, how do we even build an array that represents every possible schedule? So let's start by thinking about the array of unique player IDs. So let's think about this array here. And I've sort of structured this so that you can imagine adjacent elements as representing a match. So for example, the first 2 indices or positions represent the first game. So that's going to be between player 0 and player 1. Then the next 2 elements represents the second game. So this will be between player 2 and player 3, and so on. So if we have this array, imagine every possible permutation of this array. So that's going to be 10 factorial permutations. So that's almost going to be every possible schedule. The problem with this is that we'll end up with duplicates. So for every matchup, for example, the matchup 0-1, there's a duplicate matchup, which in this case would be matchup 1-0, where these are really it's the same 2 players, so it's the same matchup. So there's actually 10 factorial divided by 2 number of unique schedules that we can consider. And to extract these, we can just say that we're only interested in matchups where the first player has a smaller ID than the second player. So how do we even build all of these permutations? And this is one of the few times that I'm going to use a tool from another package. So to do that, we're going to say from itertools import permutations, and then we'll build this perms array using np.array list permutations and then the list of unique player IDs. And then we can go ahead and print perms. Now this does take a second to run, but when it's finished, you'll see that we have this really big array. It's going to have 10 factorial rows of every permutation of these IDs. So the next thing we're going to do is we're going to partition that array into 2 matrices that represent player 1 and player 2 for each game. So player 1 is going to be the player at indices 0, 2, 4, 6, and 8. You can kind of see that in this example we gave up here. And player 2 is going to be located at indices 1, 3, 5, 7, and 9. And then the matchups we want to keep are going to be the ones where player 1, his ID is less than player 2's ID. So we'll say keeps equals np.all, p1 less than p2, and we're going to check that along axis 1. And then we'll set p1 as p1 square brackets keeps and p2 as p2 square brackets keeps. So basically that's going to pick out the permutations where player 1 is less than player 2 for every game in the presented schedule. Okay, so it's going to cut this matrix in half, basically. Okay, so then we want to build a matrix where ij gives the expected point differential for the jth pairing in the ith schedule. So what we do here is we use this score diffs array here, and we already have the indices for player 1 and player 2. So just to get the point differentials, all we have to do is say score diffs, square brackets, and then we'll use P1 to get sort of like the row index and P2 to get the corresponding column index. And let's go ahead and print this out. Okay, so these are the point differentials between pairs of players. And then we want to get the sum of squared point differentials for each potential schedule, so each potential set of matchups. So what we'll do is we'll say schedule scores equals np.sum, and then we're going to take the squared point differentials, and we're going to calculate that sum along axis 1, so along the column axis. So we get back this big array of squared score differentials. And then we want to find the schedule that has the smallest sum of squared point differentials. There could be multiple ones, but we're just looking for one of them. So we'll say best index equals np.argmin schedule scores. And that'll give us the index of the smallest value in this array. And then we'll set the best. So actually, let me do this first. Okay, so apparently the best schedule happens at index 16,490. So then to represent the best schedule, basically we identify the who player 1 is for this schedule, or the set of player 1s, and the set of player 2s, and we'll just stack them vertically with vstack. So once we do this, we can print the best schedule, and we can see that it's player 0 versus player 7, 3 versus 6, 1 versus 8, and so on. And just to do a sanity check here, let's take a look at player 0 versus player 7. So player 0 versus player 0, 1, 2, 3, 4, 5, 6, 7. Well, they have a score difference of negative 2.15. I mean, if you look at this whole matrix, you can see that's a pretty small number, so that's a good sign. Let's check player 3 versus player 6. So we have 0, 1, 2, 3, 0, 1, 2, 3, 4, 5, 6. So their predicted point differential is 2.24, another pretty small number. So it looks like we did this correctly, and we can have the most fun, most optimal start to our table tennis league. Given a 1 million element array where each element is a random character in A to Z, identify the starting index of every sequence of characters that spells Waldo. Twist: include sequences where 4 of the 5 characters match. For example, Wafdo and Zaldo, but not Wadlow. Okay, here's the solution that I came up with. And let's go ahead and break it down. So the key to this solution is this Windows array. So let's go ahead and take a look at this guy. So Windows represents 5 character sequences from the chars array. So for example, the first row in Windows is ARPBX, which is the first sequence of 5 characters in this array. The second row in Windows, RPBXF, is the next sequence of 5 characters. And notice that it's only 1 character offset from the first sequence of 5 characters. So the way we build this array is we use the asStrided function, where we tell it we want to build a view from the chars array. We want the shape of the output to be the length or the number of characters in chars minus 4, because that's how many sequences of 5 characters we can get, by 5 columns, because we want to look at sequences of 5 characters. And then the strides parameter here, well, wherever you are in the Windows array, we basically tell NumPy that to get to the next row, it needs to look across this many bytes of data, where chars.strides square brackets 0 is just the number of bytes in any given element. So if we're at element P, to get to the next row, we're basically telling NumPy to only move across one element, or to sequence or iterate across one element. So that's why rows go just offset one element from each other in the chars array. And then of course we do the same thing for columns, because they're just offset one character from each other as usual. So the next thing we do is we build an array called waldo with the characters in the word waldo. And then we want to compare these characters to these characters. So we want to compare waldo to windows. So we say windows equals waldo, and we get back a big boolean array like this, where, for example, the first false value here means that w is not equal to a. And we're interested in rows of this boolean array where at least 4 of these values are true. So those are going to be cases where at least 4 letters in waldo match the letters in the windows array. So we'll say windows equals waldo dot sum across axis equals 1, so across the columns, and we want to pick out indices where those sums are greater than or equal to 4. Now this is going to return a tuple, and since this array here is just one-dimensional, we're only interested in the first result in that tuple, so we'll say square brackets 0. And this is going to give us the indices of what we want, the cases where at least 4 of these characters match a sequence in the windows array, which are just sequences of 5 characters. Now, if you want to check this, you can run a little block of code like this. So we'll say for index and start indexes. Okay, so we'll assign this to the value start indexes. So for index and start indexes, we'll just print empty quotes dot join cars between start index and index plus 5. And you can see that these do indeed pretty closely match waldo, like waldo, wallio, walfo. And if anybody's expecting a child on the way, maybe this is a neat little set of potential names for your future kid. Especially if you're a celebrity, I think these would go over really well. Calculate the element-wise outer product of 2 matrices A and B. So the result should be a 10 by 3 by 5 array, where the first submatrix should look like this, because it's the outer product of the first row in A with the first row in B. All right, so if you did some Googling for this problem, you may have stumbled across this Stack Overflow post, which is completely where I got this problem from. And I have 3 solutions, but the first 2 solutions, I give total credit to Dvarkar. Hopefully I'm not butchering that name too badly. But he came up with 2 very elegant solutions, and then I have a third solution as well. So I kind of have those solutions organized like this, which I will copy and paste. And then I'm just going to talk about the basic strategy for each of these guys. So the first one uses broadcasting, and A initially is a 10 by 3 array. So you can see that here. And so if we do A square brackets and then ellipses, this is equivalent to saying A square brackets colon, comma, colon, but it's sort of like shorthand notation, comma none. Well, that's going to insert a new last axis into A, and it's going to convert it into a 10 by 3 by 1 array. And then B is a 10 by 5 array, but we give it a new second axis. So we convert it from a 10 by 5 array into a 10 by 1 by 5 array. And then when we do this multiplication between this modified version of A and B, you can imagine that A, the 10 by 3 array A, gets copied 5 times along the last axis to conform to B, which gets copied 3 times along its second axis. So if you just pick out a single row, let's say like the first row here, this guy gets copied 5 times along the last axis, and this guy here gets copied 3 times along the second axis, and those get multiplied, and that produces the outer product of the first element of A and B. And so hopefully you can kind of see how this works out to produce an element-wise outer product. Now, the second solution here uses an Einstein sum, and I like to write these out in pseudocode. So the subscripts I and j correspond to the rows and columns of A. The subscripts I and k correspond to the rows and columns of B, and the subscripts I, j, and k correspond to the indices or the axes of the output. So what I'll say in pseudocode, you could write this out as initialize output as an array of zeros with shape. Well, I is going to span 10 different rows of A, so 10. J is going to span the 3 columns of A, so it's a 10 by 3, and then K here is going to span the 5 columns of B. So we initialize an array of zeros with shape 10 by 3 by 5, and then we iterate over each unique subscript. So we say for I, for J, for K, and then we set output underscore IJK. So the IJK element of the output, we set that as plus equals A IJ times B IK. And I realize this is probably a little confusing, but if you just take the time to work this out in your head and maybe fix I to some particular row of A and B, you can see that this is indeed the outer product of A and B. And then the last solution, which is the one that I came up with, is to use the as-strided function, where basically if you think about the output, and let's think about a particular element of the output. So we'll say, output IJK. Well, this is equal to some element of A times some element of B. And so if you imagine we can reshape A into an array that is the same shape as the output. So we want to reshape A into a 10 by 3 by 5 array, and we want to reshape B into a 10 by 3 by 5 array, then output IJK we can say is equal to AIJK times BIJK. So that's really the strategy to this solution. And the function as-strided, if we pass in the correct parameters, we can create a view of A where the IJK element of A points to the correct element of A that we would want to multiply with the corresponding element of B to get to the corresponding output element. And so since these are not actually A and B, they're views of A and B, we'll call this AS and BS, and their product will give us the element-wise outer product. So hopefully that wasn't too confusing. I didn't want to go into too much depth because I talk about each of these topics in the course. And if you're confused on any one of these, you can go back and look at the details in the course. But one last thing, so if we want to just see these in action, it's kind of interesting to think about which one of these solutions would be fastest. So we can use the magic command %timeit and then do something like, so I'll say OP1 for outer product 1 equals outer prod broadcasting A comma B. And we can see how long this takes. And then we can do the same thing for the einsum and for the stride trick version. And you can see that the broadcasting and the Einstein sum are basically equivalent. This one's a little bit faster, it seems, but they're more or less the same. And then the stride trick is actually significantly slower. So tip your hat to Devarkar, who came up with those really good solutions.